To start off, let's see some basic anatomy of a neuron. First, we have the little tentacles of the neuron that are going to receive messages from other neurons, which are called the dendrites. Moving down the neuron, a cell body that is going to be by the name of soma is in charge of packing the proteins of the cell and carrying other specific cellular processes, since it has a nucleus, a mitochondrion, an endoplasmic reticulum, and other organelles like every other cell. Moving deeper into the cell, we will find the axon, which is in charge of transmitting the nerve impulse all the way to what are called the axon terminals. And these ones are going to connect to the dendrites of other neurons to relay the messages. Dendrites receive, axon sends. As you can see in the image, we have the axon surrounded by some sort of wrapper, which is called the myelin sheet, and its function is to speed up the neuron's electrical impulse along the axon. Some neurons do have this myelin sheet, some neurons do not have this myelin sheet. Your body is basically electrically neutral, meaning that it has equal amount of positive charges and equal amount of negative charges. But some specific locations are more negatively charged or more positively charged than others. That is why we have membranes to separate these charges, because positive and negative charges attract each other. And so what happens is that we use this energy that the charges create because of their attraction to build potential. Think of it this way. A battery, it has a positive and a negative charge. And by itself, it's not able to function, right? But if you plug it into something, just say, I don't know, your phone, a computer, or something else, your battery will be able to trigger those charges so they can move along the way to generate the output, which is in this case turning on your phone, your computer, etc. Right? So by the same way, your neurons work like this, but the thing is that with your neurons, you need a stimulus, something that triggers the charges to come together to create the action potential. Let's check this out. Now, your neurons at rest, meaning they're just existing in the universe, have more negative charge in the inside of the neuron than on the extracellular outside part of the cell. This difference in charge is called the resting potential, which is measured at approximately -70 millivolts. Remember that your nervous system has electricity and is measured in millivolts. Millivolts because your neurons are really, really, really tiny. This difference in charge has to do with the ions in the neuron. Since in the inside of the neuron, there are less positive ions, in this case potassium ions, and in the outside of the cell, more positive ions, in this case sodium ions, the neuron's interior charge is said to be overall negatively charged. The neuron at this moment at rest has a negative membrane potential, meaning it is polarized. This electrochemical gradient is created by one of the most important machineries of the human body, which is called the sodium-potassium pump. The sodium-potassium pump is located in the membrane of the neuron. So it happens that this pump, with the help of ATP, for every 3 sodium ions that the pump lets out of the cell, the pump will move into the cell 2 potassium ions. This difference in charges and in concentration of ions is called an electrochemical gradient. Now, the movement of ions across the membrane is key for the communication of the neuron. Since nature hates gradients and wants to even out all inequalities and restore balance, the only way that this could be achieved is that if the ions cross the membrane. That is why there are ion channels that sit on the membrane of the neuron that can let in the flow of ions, and they open or close because of different reasons and because of different scenarios. For example, there are ion channels called voltage-gated channels that open or close depending on the changes on the membrane potential. For example, when the neuron reaches -55 millivolts, these ion channels open. Another type of channels are called ligand-gated channels, and they open when specific molecules attach to the channel. For example, a neurotransmitter, a hormone, etc. In order to generate an action potential, a great change in the membrane potential first needs to occur. For example, if only a few sodium ions cross the membrane, becoming it less negative but not enough for the action potential to occur, then the action potential will not be generated. This is called a graded potential. Remember, the threshold for the action potential to occur is negative 55 millivolts. If the membrane potential does not go and does not reach that threshold, then the neuron will not fire the action potential, and therefore the neuron will return just to its normal state. You're sitting alone in your couch and your neuron is at resting state of approximately negative 70 millivolts. Then all of a sudden a spider comes to your leg, and that triggers the opening of ion channels in your neuron to open and let into the neuron sodium ions, which that will increase the charge inside the membrane. The stimulus, the spider in your leg, has to be strong enough to be able for the membrane to depolarize. Depolarize, meaning to the cell membrane become less negative in its interior. Once the membrane potential reaches negative 55 millivolts, then what will happen is that the action potential will start. Voltage-gated ion channels will let the influx of sodium ions into the interior of the neuron, and the interior of the neuron will depolarize all the way to approximately positive 40 millivolts. An action potential causes a fascinating biological chain reaction that will send the electrical impulse all the way along the axis. Neurons in the membrane have a humongous amount of voltage ion-gated channels, and so what happens is that once one opens, this one will let the influx of sodium ions, right, as we said earlier, into the cell's interior, right? And this great amount of positive charge will let another voltage-gated channel to open, and then the other one will let another one to open, and so on along the axon. Now, if you paid attention, we said earlier that the myelin sheath, like the wrap around the axon of the neuron, will let the neuron's electrical impulse to go faster along the axon. What happens is that a neuron that does not have a myelin sheath insulated in them, they will usually go and trigger one channel at a time, creating the biological chain reaction. But neurons that do have the myelin sheath, what they will do is that they will create what is called a saltatory conduction. Saltatory conduction is that the electrical current will go and leap from one gap of the myelin to the next. And these little gaps are called nodes of Rambier.